Welcome to this webinar on machine learning with decision trees organized by Edureka. And my name is Shiraj, and I typically teach data science classes as well as big data, Hadoop, and Spark classes in Edureka. But in my professional life, I'm also working as an architect in the space of retail domain. I'm currently working in California, USA, and I've been working in this big data and analytics space for more than 10, 12 years. I have done my PhD in this area and working on analytics and data management in combination. Okay. And day to day, we use a lot of machine learning problems to deal with business issues that we see in retail space. Things like recommendations, demand forecasting, supply chain management, and those kind of things. So you can pretty much kind of see the applications of machine learning in a variety of domains and variety of applications. And retail is just one of them. So that's kind of briefly about me. So today's session, we are going to simply talk about the basics of machine learning. We start by understanding what exactly it means and what are the high-level types of machine learning. And then we'll focus primarily on one of the technique called as predictive analytics. That's the class of machine learning algorithms. And among those class of algorithms, we will look at decision trees as one particular example. Okay. And meanwhile, if you have any questions, please feel free to type in your question and I'll respond to it whenever it is appropriate. And by default, all of you would be muted, so you would not be able to speak. Again, if you want to speak up and elaborate on a particular question, request me to unmute you, and I can unmute you, and then we can speak online. Okay? And feel free to ask any type of questions. I strongly believe that no question is a bad question. Okay, so ask any question that you want related to machine learning in general, data science, or artificial intelligence, or any specific question about the particular topic that we are talking about. Okay, so that's pretty much outline for today's webinar. We start by talking about what is machine learning, and then we'll look at a class of techniques called classification, which is also popularly known as predictive analytics. And then we'll talk about decision trees, and we'll see some details about that particular technique just to get a sense of how predictive analytics technique can work in real world scenario. And then I'll also show some brief demo of this particular algorithm in the context of our programming language. Okay. So to begin with, what is machine learning, right? And if you look at Wikipedia, it says machine learning is a subfield of computer science that provides computers with the ability to learn without being explicitly programmed. And this was a definition, there's not really a particular definition of machine learning, but this is what one of the scientists said back in 1959. So you can see how old is this branch of computer science. In fact, the father of computer science, who's Alan Turing, if you have seen Imitation Game movie, the name Imitation Game is actually proposed by that father of computer science, and that's kind of considered the birth of artificial intelligence. He imagined a computer or a software or a program that can mimic as if it's a human being. And that's kind of the higher level idea behind artificial intelligence. Can we make machines smarter, right? And artificial intelligence is a huge umbrella of variety of techniques, and machine learning is kind of can be considered as a subfield within this umbrella of artificial intelligence. Okay, and just to give you a more concrete example, imagine we're trying to write a computer program, developing some software that can recognize human faces in a given picture. Okay, very simple, right? Especially given that Google Photos, for example, can easily detect human faces, right? It became such a common technique in our real world. But if you think about it, how would you develop such a software, right? If you kind of spend some time thinking about it, you can see that there are two types of approaches that one can develop to design this face recognition software. Okay. One thing, as a programmer, we are going to encode all the features of a human face, right? We'll kind of program how does a human face looks like. It's in kind of round or oval shape and with hair on top, ears on the side, with particular structure of ears. There's a common structure, right? And there's two eyes on the top and then nose and stuff like that, right? All encode all the characteristics of a human face and then write it as a program. And in a given image, the program will simply look for these characteristics. If they are present, then image is tagged as human face, otherwise not. Okay, that's one way of writing that software. But is there learning in it? If you think about it, we are not really learning anything. As a computer programmer or as a software developer, I am taking the whole burden of telling the computer how a human face looks like, right? All that program is doing is automating those checks, right? So there's not really learning in it. So that's the first style of approach, which is not really machine learning. It's not really learning anything from the data. Whereas the second approach, which is kind of considered as machine learning, operates like this. We provide this software a variety of examples of human face images as well as non-human images, something like a mountain or a landscape or a bird or something like that, right? So we mix human faces and non-human faces, right? And we give all of these as examples to the software. And we'll also tell the computer or tell the program that, oh, this image has a human face and this one does not. So for every image, we also provide a label which says whether it's a human or not human. And then the software should be able to distinguish between these two types of images. It should learn the different characteristics that are present in human face images and not present in non-human images, right? So it is able to learn the distinguishing features between these two classes of images. That is a setting of a machine learning algorithm. And if you imagine, that's how we also learn as humans, right? I mean, if you think about a 2-year-old kid, right? When they were born, they have no idea how a dog looks like or how a human face looks like, right? But if you read to them, show lots of books with different pictures saying that, oh, this is a dog, this is a cat, this is a dog, this is a cat. And after seeing enough examples among, let's say, 20 different books, they start to make a mental picture of how a dog looks like, right? And when we show 20 different books, not all the dogs look the same. Different dogs are different breeds and different sizes, different shapes. But still, the human brain is able to capture the distinguishing features of the dog face. And then suddenly one day you show some other random dog picture and they'll be able to recognize that this is a dog and not a cat, right? So human brain, just by looking at lots of examples, it is able to figure out the differences between something that we want and something that we don't want in a particular task, right? So that's the machine learning. That's exactly, I mean, that's human learning, and that's exactly how machine learning techniques also operate. You give lots of training data, which is examples, okay? Just like we are showing the kid lots of images about dogs and cats and human faces, we give lots of examples to the computer program. And then the program is able to learn the differences between different classes of data points, whether it's images or audio samples or credit card transactions or whatever, right? And then it builds the mental model, whatever we're building in our brain, it builds something like that called as a model, which kind of denotes how a human face looks like, how a dog face looks like, or how email spam looks like, right? So that's the model building. And then we use that model in production to do actual tasks in real world, in practice. And then as it does, we also get some feedback and then continuously learning from the feedback, whether we made a mistake or not, right? That's how, again, our brains also learn. Not first time, the kid may not recognize all the dog faces. Sometimes he makes a mistake. And then we correct the kid, saying that, oh, no, 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 this is actually a dog face. Then the brain improves by getting that feedback and then improving the mental model. That's exactly the feedback loop that we are seeing here. So you can clearly see the analogies between the way our human brain works and the way machine learning models also work. It's exactly the same. It's kind of mimicking that process through computer programs, right? I hope that is clear about what a machine learning technique would entail, right? How is machine learning and artificial intelligence related? Yeah, as I said, artificial intelligence is a much broader spectrum of techniques, and machine learning is one part of it. Okay, like if you look at something like self-driving cars, there's a lot more artificial intelligence than just machine learning. It's a different type of setup of a problem and different type of techniques that are used. So yeah, machine learning is kind of, you can think of it as a subset of artificial intelligence, purely in terms of the number of techniques or type of techniques. Okay, and like face recognition and voice recognition, you can come up with so many examples that we see in real world that are relating to machine learning, right? Actually, we are surrounded by machine learning applications in our everyday life, right? Like as soon as I go to google.com, there are lots of advertisements, and those advertisements are tailor-made for my browsing behavior. Yesterday, I searched for, let's say, Nike shoes, and then suddenly I start seeing Nike ads while I'm browsing, right? That's essentially learning from my browsing history, and then tailor-making the advertisement for my needs. That's one example. And as soon as I open my Gmail or any mail, right, I see only nice emails addressed to me, not the spam anymore, right? If you think about emails, let's say 15 years back, there used to be a lot of spam coming into our inbox as well, right? So, but nowadays we hardly see spam in our inbox because the email filters have become so matured in terms of differentiating between spam and non-spam. That's again a machine learning application, right? Given a email, how does it know? How does the email filter know that this is a spam or not a spam? That's again learning. And 15 years back, those algorithms were still learning, but now they are pretty much very mature, and therefore they are able to make very good decisions, right? So that's one example. And similarly, a lot of recommendations that we see on, let's say, Amazon.com or Flipkart.com, those kind of e-commerce websites, right? What kind of data do they have? They have consumer demographics, right? What's the age of the person, gender of the person, location of the person. If the data is missing, they try to interpret based on, again, other browsing history and other things, right? And also, they have the purchase history, what kind of items that you have bought in the past, and what kind of items you have looked in the past, what kind of items you clicked it but not bought, right? They pretty much track each and every interaction that you make on that website. And using all this data, they try to recommend certain products to you that are hopefully suitable to you, right? And Amazon has pioneered in this recommendation systems, and nowadays recommendation system is like the most common applications that you can think of in every single business. Whether you are an insurance company, whether you are a bank, or whether you are a medical product provider, everywhere you can think of cases of recommendation engine, right? And that's also machine learning example. So you can kind of look at many examples of machine learning surrounding us in our everyday life, right? And there are many types of machine learning tasks. And one most popular one is the predictive analytics, also known as classification. Okay. And in fact, like the examples that we talked about, or a couple of them are about classification, like face recognition to begin with. What is that program doing? It is able to classify a given image to be a human face or non-human face. So that's a classification. Okay. Similarly, email filter. It is able to classify a given email to be spam or non-spam. That's again classifier. So you're taking the data and then dividing it into different classes, different categories. Okay. And that's the classification. And it's also called as predictive analytics because you can think of it like you're predicting whether a given incoming email to be spam or non-spam. You're predicting that, right? You don't know in reality when a new email comes. It's only your prediction. But then since your learning is so mature that your prediction is pretty much always true these days, right? And since you're predicting, it's called as predictive analytics, right? And that's essentially that. Classification is a problem of identifying to which set of categories a new observation, new data point belongs. And that data point can be an image or an email or a credit card transaction or a medical profile of a particular patient, right? Whatever is your data point in your application, okay? And we are able to learn the differences between different categories of data, provided lots of example data, right? During the learning time, you need to provide lots of emails, and then for every email you need to say, oh, this is a normal, genuine email, whereas this is a spam email. So you need to show millions and millions of examples, and then the more data that you feed, typically the better it becomes, right? Just like our brain. When I'm learning a new concept, let's say in mathematics, differential equations, the more examples I practice, the better I become, right? But after a point, there's a saturation. After a point, I'm pretty much know differential equations in and out. Exactly like spam filter. After a point, the learning kind of flattens, right? Can you please give some other examples on predictive analytics, maybe an industry example where decision is taken? Yeah, actually, I mean, spam filter is a real world example, right? Google does it or Yahoo does it. And let's say credit card transactions. Whenever a credit card transaction comes into the banking system, they have to make a decision whether that is a fraudulent transaction or a genuine transaction, right? And if it is something fraudulent, they predict it to be something fraudulent, then they immediately reach out to you. Like nowadays, at least in US, I don't know how credit card companies work in India, but in US, let's say I'm always using my credit card in my area in California. Suddenly, when I go to India and then swipe my credit card, immediately I get an alert saying that, oh, are you the one trying to swipe this card? Is this genuine or not? And then I have to say genuine, and then it will approve, right? So that's like a alert system because it predicted that there's something fishy about this new transaction because it differs so much from my existing history of transactions. So that's a predictive analytics as well. And like that, you can come up with many examples, like another things like in medicine. When a patient profile comes in, you can feed it to these machine learning models and then predict the risk of having certain disease, right? And in the later part of the class, when we see the demo, we'll see the data set where you're predicting the risk of having diabetes, right? So that's essentially a prediction problem again, classification problem. And if you go for, let's say, MRI scan or a bunch of other tests, there's always certain probability associated with the outcome of that result. They'll say 99% this test is accurate, right? And a lot of, I think, heart-related diseases like blockage of heart valves or whatever, arteries, the tests that they make, MRI, CT scan, those kind of things, in fact, they only have 75% of accuracy, I think, somewhere around that number. What that means is it is trying to predict something based on the images that it scans of the heart, and then it predicts whether this is actually a problem or not a problem. But then the accuracy is very low. It's only 75% accuracy. That means 25% of the time it makes bad decisions. Even though there's a problem, it may not detect, or the other way around. It might falsely say, oh, this patient may have a risk, so you better go for additional tests, more involved detailed tests, or do something else, right? So those are all, in all of those scenarios, there is predictive analytics hidden behind it, okay? And similarly, like Airtel, for example, every day they want to figure out which customers are likely to go out of my network and then join another network. That's called churn, right? That's again prediction, because I'm trying to predict who is going to leave my network. Okay, does that make sense? Okay, very good. And so those are the different applications where this predictive analytics can play a role, right? But how do we actually learn? How do we build that mental model, right? Like, for example, if I'm like a middle school student and or elementary school student learning how to divide two numbers, right? Dividing two numbers is a task, just like predictive analytics, predicting whether email is a spam or not. That's a task. And to learn that, there are multiple different ways, right? In Japan, they teach division in one way. In India, they teach division in a different way. And somewhere else, they might teach in a different way. But ultimately, it is about learning the task, right? So there may be different methods of learning the same concept to build the same mental model to divide two numbers, right? Similarly, in order to learn these predictive models, the models that can predict, there are a bunch of different techniques, okay? And in fact, there are, like, just for predictive analytics, there are like more than 10 different techniques. And every day people come up with their own twists on a popular technique as well, right? But most common things are decision trees, which we are going to see today. And then another related technique is random forest. And then another one is called naive Bayes. But there are also other things like linear regression, logistic regression, support vector machines, neural networks, right? Or deep learning. Nowadays, that's a very popular term as well. So all of these are some form of predictive analytic techniques, okay? And to make the problem even more interesting or frustrating, for a given data set, for a given application, one algorithm may be better than the other algorithm. We cannot say that decision tree is always the best algorithm compared to naive Bayes, right? I can always come up with a data set where naive Bayes performs better than decision tree, or the other way around, right? So for a given data set, you have to figure out which of these algorithms work the best. So how can you do that? Only by trial and testing. So you, for a given data, you apply decision tree algorithm, you get certain result. You apply random forest algorithm, you get certain results. You apply naive Bayes algorithm, you get certain results. And then you choose the one that gives you better result, better accuracy, right? Accuracy is one metric by which you choose your algorithm, but then you also can see the engineering effort in making this algorithm run in production, right? That may be another metric in terms of making it actually work in production. And with respect to that, maybe one algorithm is better than the other, even though its accuracy is slightly lower, right? So there are a bunch of decision factors through which you go about choosing a particular algorithm for your particular application, okay? So it's all depends on data. And another related fact is you feed in the quality of the results that you get primarily depend on what kind of examples, what kind of training data that you provide, right? Again, to draw an analogy, if you teach the student by showing good examples of differential equations, then the student will learn better. But if you show very simple examples always, or some nonsensical examples, then the mental model that the student is going to build may not be that strong, right? If you don't show all the intricacies in all the corner cases in differential equations, then the knowledge that the mental model is going to learn is also very limited. So it all depends on what kind of data that you feed into the algorithm, right? You feed in junk data, you get a junk model as an output. you feed very good quality data, you get very good model as an output, or you're likely to get a good model as an output. Okay, so the quality of the model depend primarily on the data as well, not just the type of technique. Okay, so now we're going to drill down a little more into what is a decision tree algorithm. Okay, so what is a decision tree? Decision tree is basically a technique or a data structure that you build that help you in making your decisions. Okay, and it's very, very common. Even though we don't call it decision tree, we all use it in real world, right? Let's say I'm a manager or an architect in computer science department in a company, right? I want to make a decision in terms of I have some requirement in my team. I need to make a decision whether I should build my own software to do that requirement, or offshore that requirement to some other consulting team, or even buy a product that already solves that problem, right? There are a bunch of different alternatives that I may have to address the requirements of my team, right? Or you may have multiple different consulting companies trying to offer a solution, work as an implementation partner. Or you may have multiple competing products that you can buy and solve your requirements, or build something on your own in-house, right? These are all different options. How do you go about finding the best solution among these all options? You basically build kind of a series of decision points. First, you may want to see what kind of effort that is required for each of these alternatives, right? And also what kind of cost you might incur, and what kind of ROI you can expect out of each of these decisions. So you kind of draw a list of decision points, and then based on those, you go about choosing the final solution or final approach to your problem, right? And similarly, let's say if I'm +2 student and trying to, or I'm a 10th class student trying to find my stream of study, whether should I take MPC mathematics background, or biology, or civics, or something else. How would you do that? For every alternative, if I take maths as my major, what are my different choices? I can do engineering, I can do, I don't know, chartered accountant, and blah, blah, blah. If I do engineering, again, I can do master's, I can do PhD. If I chartered accountant, I can do, I don't know, practice in a good firm, something like that. So you have a tree of different alternatives, and then based on your final outcome, maybe expected income after 20 years, just throwing it out as an example, based on that outcome value, you're going to choose which of these paths I need to take, right? That's kind of a decision tree, a tree of decisions that you have, and then you're going through these tree of alternatives, finally reach a particular path of career, right? So decision tree is very, 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 very common, and it looks pretty much like that, a simple tree, right? Here I'm simply seeing, oh, what is the gender of a particular data point. If it is female, go to the left. If it is male, go to the right. If it is female, check the income of that particular person. If it is less than something, go this way. Greater than something, go this way. And then you make finally a decision. Something like email is a spam. Email is not spam, right? Or this is a human face and this is not a human face. So that's a decision. So it's a series of alternatives you're exploring to reach a particular decision point. So that's the decision tree algorithm. Okay. And this is also, you can think of it as a prediction, right? If gender is female and income is less than something, I'm going to predict some outcome, right? If my email is not from a known sender and the email contains words like Nigeria and I don't know, some lottery or things like that, then I classify that as a spam. That's kind of a decision tree, right? First check if it is known sender or not, given my history. If yes, go to the left. If no, go to the right. And if no, check if the email contains the word Nigeria. If yes, go to left. If no, go to right. And then again, if it is yes, then see if it is talking about bank accounts. If yes, then classify it as spam, right? So that's the kind of decision tree that we are talking about. Okay. And similarly, you can talk about many different examples. Like this is another example, which is very real world application, as one of you were asking. It's a credit risk detection, right? When somebody is giving you, a financial institution is giving you a loan or a credit or something, they analyze the risk, right? Whether you can pay back that particular loan, or you can pay back EMIs on time, right? They analyze the risk. And there are lots of softwares just for doing risk analysis as well. But you can, and this kind of technique can be one of those techniques in that suite of software that analyzes risk. So you see what's your income of a person. Depending on income, you may check what's the credit history of that person. Especially in US, credit history is very, very important. Credit score, right? If it is good, or if it is bad credit history, but your income is very high, then you have kind of moderate risk. So since your income is very high, maybe it's okay. But if your income is is kind of average, and you have bad credit history, then suddenly you become like a high risk customer and you may not get a loan, right? So that's again like a decision tree. Based on different characteristics of that particular application, you're making a decision whether this application has high risk or low risk or medium risk. Okay. So to understand a little more, let's take a concrete example, which is a very, very toy example. In fact, this is an example that was given by the inventor of decision trees in his original paper. His name is Kinlan. Yeah, this guy, Ross Kinlan. When he proposed this algorithm for decision trees, he used this example in his paper. Okay, what is this example? I have a bunch of data points, okay, about whether I should decide to play outside or not, outdoor playing. And how would I go about deciding whether I should play outside or not? Depending on the weather, let's say. I'm going to look at three features. Okay, that means three properties based on which I'm going to make decision. Those are called features of my data. And what are the features? What is the outlook? What's the outlook for tomorrow? Is it going to be sunny or raining or overcast, like cloudy or something, right? And the other thing is, what's the humidity level? Whether it's high, normal, low, whatever are the values. And then also, what's the wind speed? Is it going to be strong winds or very mild winds or moderate winds? Whatever, right? Different values. So based on these three attributes of tomorrow's weather, I'm going to decide whether to play outside or not, right? That's the decision variable, yes or no. Okay, these are my training data. For every record, I also have the outcome associated with it, like spam, not spam, fraudulent transaction, normal transaction, play outside, yes, play outside, no. Okay, so that's my training data. When a new data point comes in, that means if I want to decide for tomorrow, I will see what's my outlook, what's my humidity, what's the wind tomorrow, wind speed tomorrow. Based on those, I'm going to predict whether to play outside or not, right? When a new data point comes in, you get all the feature values, but not obviously the label value, because that's what we are going to predict. Okay. So I have weather information of last 14 days, and I also have the decisions that we have made. Okay. Whether we played or not played. Okay. Not just the decisions, whether we actually played or not. That's the actual data, right? And then we can predict for future based on those 14 days of data set. Okay. So this becomes our training data. Now using the training data, let's see how to build a decision tree, right? If you look at our previous examples, how does it look? I'm going to check different properties, different features. First, I checked income here. Then I checked credit history. Then I checked whether the person has debt or not, right? These are all the different features. So similarly, in our data set, we have features like outlook, humidity, and wind. Okay, so let's take Outlook to begin with, and let's see what are all the different values of Outlook. Okay, what are the three values? It can be sunny, it can be overcast, or it can be rain. Okay, so those are the three possible outcomes if I look for Outlook. Okay, so what that means is if tomorrow's Outlook is sunny, I go to the left branch. If tomorrow's Outlook is overcast, I go to the middle branch. Otherwise, I go to the right branch. And in my total data set, there are 9 yes records and 5 no records. Okay, these are according to the label that we have. Okay, and now we will see how these 14 records, 9 yeses and 5 nos, will get distributed across different alternatives. Very straightforward, right? So out of all these 14 records, how many of them have sunny, and how many of them decide to be overcast, and how many of them are raining? Okay, you would get like this, right? It's simply dividing the data set according to different outcomes of Outlook. Now let's take a look at this data set. Let's take a look at these partitions of the data. Okay, so if you look at the first partition, look at yes and no combinations. Okay, there are 2 yes records, the ones mentioned in green, and then 3 no records. Okay, that's what you will see in if you go step by step in the data as well, right? Take a look at sunny, 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 3 reds, and then sunny, sunny, 2 greens. Okay, that's what we have here. 2 greens and 3 reds, 3 no records and 2 yes records. And then if you look at all the overcast, everything is green. That means in the last 14 days, whenever there was an overcast, I was playing outside. Okay, and then rain, again you can see there are 3 yeses and 2 nos. Okay, but there is an interesting characteristic about this middle guy. What is this saying? It's all saying play. So what that means is, based on our historical data that we have, if the outlook is overcast, I don't know to look at whether wind speed, whether it's going to be high temperature or low temperature or humidity. I don't care about anything else. If outlook is overcast, I'm going to play, right? So we reached a decision right there, one of the decision. So if you come and tell me tomorrow is going to be overcast, then I can immediately say, oh, according to my data that I have seen so far, that I learned from, we can play tomorrow. But then you will come and say, oh, tomorrow is going to be sunny. Then I say, oh, if I look at my old data and I expect the similar behavior in the future also, then I'm not sure, because my data is not convincingly telling me to play or not, right? Maybe we need more variables. Oh, now I'll say, oh, tell me the temperature also, or tell me the humidity level. Let me see if that helps, right? Just based on sunny, I cannot make a decision. So I try to go further. I want to split further. Okay. And similarly, if you say tomorrow is going to rain, again, I'll say, oh, that's not good enough for making a decision. Tell me about humidity, or tell me about some other property. Okay. So that's the idea. Now, if you go further, you can split further. So if it is sunny, I will ask you, oh, tell me humidity, whether humidity is going to be high or normal. If it is high, my data is telling convincingly it's a pure subset. That means all or no records. There's no mix. So if tomorrow is going to be sunny and humidity is high, then according to my data, I can tell that we shouldn't play. But if tomorrow is sunny, but humidity is normal, then again, according to my data, we can play. I'm emphasizing on according to my data because the decisions that we are making is completely based on what data that we have. Instead of 14 days, if I give you 30 days of data, maybe the tree structure that I'm going to get will be completely different. Maybe or may not, right? But they can be different. So you always try to make a decision based on what data that you have seen. That's why I'm keep on emphasizing according to my data. Okay? And similarly, rain, we have a mix here, so we try to split further. Then again, in this case, probably I want to check wind. It's raining, but if rain and wind comes together, that's a deadly combination. So I don't want to play. But if wind is weak, normal winds, then maybe I can play. Okay, again, according to my data in the past. So that's my pretty much decision tree that I built, right? Now you tell me any day's forecast, outlook, humidity, and wind combination. I can tell you whether to play outside or not, right? Can you do that? We all can do that. We simply need to go over different branches and then finally reach a leaf node, the last node, where the actual decision is made. This is not play, this is play. Play, play, not play, right? That's pretty much decision tree for you. But this is again a very toy example, and then we are trying different combinations. But then we made some assumptions, meaning, why did I look at outlook to begin with? Why didn't I look at humidity or wind level, right? Those are perfectly possible alternatives. And again, here, once I know outlook is sunny, why did I check only humidity? Why not wind or some other feature that may have temperature or something else, right? So then the question comes, these are great. I mean, this is my final decision tree if I remove my data. But how would I know which attribute should I take at any step in the thing, right? So there should be some math behind it that drives our decisions or drives our choices in terms of which attribute to inspect on, okay? And this is another example just to give you more variety. So hold on to that question. We'll come back to that question, or we'll try to answer this question of which attribute to take in the context of this example. So what is this example? It's just a case of a bank that wants to market its products to different customers. Okay, and then see whether the customer is gonna subscribe to that particular product or not. Okay, and we are going to predict whether the customer is going to subscribe or not based on certain features, certain attributes. So subscribed or not is our output column or the result column that we are interested in, that we want to predict. And we want to predict the value for subscribed based on all these different things. Okay, some demographics of the client, like marital status, education, housing, does the client has house or not, loan or not, what's the type of contact, what's the previous outcome in my interactions with him, and then what's the job area that he works in. Bunch of some features about that particular client, right? Based on those things, I want to make a decision. Of course, I need to start with some training data. That's the training data with some examples of features as well as the outcome that I have observed in the past. Okay, with this, now I have to construct a decision tree. So obviously the question is, should I first look at job, marital status, education, housing, blah, blah, blah. Which one should I start with? And this is only how many I have? 7 columns I have, 7 features. 1, 2, 3, 4, 5, 6, 7. And then one output column. But in real world, like if I am looking at email data, the features that I can construct would be thousands. So out of all these thousands of columns, I have to choose which one to begin with. And then at every step, right? Not just in the first root node, but at every step, I have to decide what column to choose from, right? So that's a decision we need to make. And for that, we have some math associated with it. Okay, what's the math tells you? The math is based on certain concept called entropy. Okay, a common way to identify the most informative attribute is to use entropy-based methods. Okay, entropy is a mathematical concept. Okay, and nothing related to machine learning. Entropy was actually invented in the context of information theory, right? Back in the time when they were trying to invent a way of communicating information, like before telephone networks came in, right? How to pass information from one place to another place in a concise manner. In that context, the entropy was first used in the context of information theory, and the same concept is used here as well. What does entropy mean? It measures the amount of uncertainty or randomness that is present in the data. Okay, it is a measure of amount of uncertainty or randomness. So what does that mean? Let's take a common example to explain this entropy concept is politics. Okay? Before the elections, there will be lots of exit polls, right? That's my data, let's say, exit polls. What do exit polls do? They go to a bunch of people, they survey whom you're going to vote, whether Republican or Democrat or BJP or Congress, assuming, let's say, there's two parties. Okay, so you get bunch of data points. Congress, 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 BJP, Congress, BJP, 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 like that, a list of preferences provided by different survey participants. Now, given this data of preferences, the entropy tells you how random that data is. What's the uncertainty? If the election is very tight, okay, in US elections, everybody predicted Clinton is going to win, but Trump won. But let's say, I don't know, some elections where it was very tight. That means 50% or 49% of the people said one party and 51% of the people said another party. So it's kind of neck to neck competition. So that is highly random, meaning you cannot predict, or highly uncertain. The outcome of that event is going to be very uncertain, right? Because it's 50-50 or 49-51 chance, right? You cannot really predict. So that's the high entropy. Okay, if my data is like that, then I will say my entropy in this data is very high. The uncertainty that is present in this data is very high. Whereas if you take our last elections in India, BJP versus Congress, pretty much every Tom, Dick and Harry knew that BJP is going to win because Congress did very badly in the previous year. So everybody got fed up with it. So if you had done the survey, 90 people would have said BJP and 10 people would have said Congress out of 100. So there, the amount of uncertainty that is present in the data is very less. It's very biased towards one particular outcome. So in that data set, I would say entropy is very less. Okay? Yeah, I'm coming there, Praveen. How entropy helps in decision making. But you get the idea of entropy? In one case, when it is neck to neck thing, entropy is very high. And in the other case, when everybody knew BJP is going to win, entropy is very less. Now you tell me, if I give you these two data sets, okay, let's take data set 1 to be US election, where it is neck to neck, and data set 2, which was the Indian election. Now, if I give you two data sets and then ask you to predict who's gonna win, pick a winner, which one do you think is easy to pick? Is US election data or the Indian election data? Which is easier to predict the winner? Absolutely. We are going to say in Indian election, where BJP got 90% of the votes, or 90% of the survey says yes to BJP, we are going to, the prediction is much more easier in that case because the majority, 90% majority is saying BJP is going to win. So you can see when the entropy is low, prediction becomes easier, right? That's the connection between entropy and the ability to predict. If the entropy is high, that means it's 49-51 vote thingy, the prediction is difficult, right? It's highly uncertain scenario, so anything can happen. I cannot predict very well. So when entropy is low, prediction is easy. When entropy is high, prediction is difficult. Agree, everyone? So that's the theory. Now, how does it relate to in this particular case? In my data set, so I can take this as two parties, right? Yes party, no party, right? No is, let's say, BJP and S is Congress, right? So these are, let's say, my survey participants. There are two S's and I don't know, 4, 8, and 12. 12 no's, right? So let's say no is BJP and S is Congress. So we are saying out of 14 participants, 12 are saying no, meaning BJP, and 2 are saying yes, meaning Congress. So what do you think? The entropy is very low, right? If I compute the entropy value according to whatever equation I have, the entropy would be very small. So this problem should be very easy to predict. Blindly, I can just say whatever data you give me, I'll just say predict no. What's the chance of error? 2 out of 14, right? That's a very small error. You see the point, everyone? So that's the idea of entropy, okay? If I compute an entropy based on the outcome values, so every outcome column has a bunch of possible values, yes, no. Or if I'm predicting the risk of diabetes, high risk of diabetes, medium risk of diabetes, low risk of diabetes. So I have 3 outcome possibilities. And in this case, yes, no, 2 outcome possibilities. So it's like a 2-party system, 3-party system. And then using this existing data, I can compute the entropy. What's the level of uncertainty that is present in the data? And how can I divide this data so that I can become smaller entropy partitions? So if I look at our original data, previous example, this is my original data, right? 9 play records and 5 don't play records. So that means 9 people voting for yes party, 5 people voting for no party. So I can do the math and compute the entropy. It would be fairly high because 9 to 5 is still difficult to predict. So what we did, we divided the data in such a way that everything is a clean split, pure subset. What does this mean? What's the entropy of this guy? Let's say this partition. Everyone is saying play. So 100% of people voted for one party and 0 voted for the other party. So how easy or difficult is it to predict? It's very easy, right? If you come here, you just say yes. And if you come here, you just say no. Because the entropy is actually 0. There's no uncertainty at all. So the point of decision tree is to divide the data set such that the entropy of the resulting subsets is smaller. Okay, does it make sense, everyone? So to begin with, in my original data, there is some measure of entropy we can calculate, okay, ignoring the equations. I just want you to capture the idea. We have some level of entropy, some level of uncertainty, but we are dividing the data such that each resulting partition has less amount of uncertainty, okay, which means easy to predict. So we are breaking up a difficult to predict problem into many easy to predict problems. That's the underlying idea of the math behind decision tree. Does that make sense, everyone? Okay, so that's it. If you understand that, decision tree is very, that's it, that's the end of it. And all you need is just a math to compute the entropy value. Ultimately, you need to compute that value, right? And that depends on the probabilities. Without going into the details, you can just plug in these probability values. Like if I say 9 yeses and 5 nos, what's the probability of yes? 9 divided by 9 plus 5, right? So if I have in my data 9 yeses and 5 nos, then probability of yes would be 9 divided by 14. Probability of no is 5 divided by 14. Those are the 2 probabilities for my outcome. Then I simply plug it into this equation and then I get a value. That's the entropy in the given data set. And then we can do some more math and say, oh, if you divide based on certain column, okay, in this example, some contact column, okay, what are the entropies of my resulting partitions? Something. Okay, there's some math. I don't want to go into confuse you more, but there is some math to figure out what's the entropy of the resulting partitions. And then you simply take the subtraction. What's the entropy before and what's the entropy after partitioning by a particular attribute? And what's our goal? We want to take a difficult to classify problem and then turn it into easy to classify problem. So we want to reduce the entropy as much as possible. So we want this difference to be as high as possible, right? Before minus after entropy, right? If the difference is very high, that means we are dividing the problems into very small entropy partitions, right? So you simply compute this difference, which is called as an information gain, that metric for all the attributes in your data, like this. If I divide it on P outcome, this is my information gain. If I divide based on my contact column, this is my information gain. So you do that for all the columns. And then you simply pick the one with maximum value. In this case, P outcome. So what that means is, given the data set, the first thing I should check is P outcome. And then based on that, you divide. Okay, like this. P outcome, whatever is the set of values. And then you make, again, same calculation. Out of all the columns, compute the information gain for this particular subset of data. And then choose the best one. In this case, probably education turned out to be the attribute with highest information gain. And you keep on doing that. And ultimately, whenever you get like a pure subset, then you say there's nothing to divide anymore. I can make a decision, right? So just with the notion of entropy, you can pretty much derive the entire technique. Okay, is that clear? Okay, so that's pretty much decision tree. And there are a bunch of pros and cons to it. I mean, sometimes it works well. There are some negative points about that data as well. There's a notion of overfitting, meaning not always you get very good prediction accuracy. So there are certain techniques to deal with that as well, which is basically biased data and training set. So that's the notion of that. And then if your data is slightly organized in different ways, then you may not get good results always. So there are a bunch of pros and cons with that technique. I mean, you would be able to understand once you drill down deeper and then try to understand the properties of that particular math. But overall, it's a very, very intuitive and easy to develop an algorithm. Okay. And surprisingly, it also performs very, very well in practice overall. I mean, in a common scenario, right? You can always find a better algorithm maybe, but typically decision trees gives you reasonably good performance for your data sets. Okay. And that's why it's very commonly used as well. Okay. If there are no questions, I can give you some demo of this particular algorithm as well. Okay, very good. So the data we are going to work with is diabetes data set, which looks like this. So I'm going to show this data set demo in R programming language. Okay, question, how important is it for data science? You mean the decision trees? So I would like to rephrase that question, because how important is decision trees for data science is actually a kind of misleading question. So you have to think of these techniques, whether it's decision trees or logistic regression or support vector machines, random forest, naive Bayes, all these different techniques are different ways of solving a problem. And the best analogy to understand that is like different tools in a toolbox, like a hammer, screwdriver, a spanner, blah, blah, right? These are all different techniques or different tools. Now, for a given task, if I want to fix something in my house, I will use a certain combination of these tools, right, that are appropriate for that particular problem, right? If I'm fixing my door, I would use a couple of tools. And if I'm putting nail in my on the wall, I'll use a different set of tools, right? Maybe a driller and a hammer and a bunch of other things. So for a given problem, a different set of tools would be appropriate. So I cannot say how important is a hammer for building houses, right? Yes, it's important. Every tool is important, right? But for a given task, some tools would be more appropriate and perform better than other set of tools. Exactly the same way. All these different algorithms are like tools in your toolbox. And that's why a lot of people also write articles saying data scientist toolbox. What does that toolbox contain? Different techniques. And for a given data, for a given problem, like if I'm predicting diabetes or predicting credit risk or predicting something else, email spam, for each of these different problems and for a given data, a couple of these techniques may perform better than the other techniques. Okay? Make sense? That's a great question. On what basis we can select an algorithm? What do you think? It's based on the performance of an algorithm. Something like accuracy. If I make 100 predictions, how many of them will turn out to be true? If 99% of them turn out to be valid predictions, then yeah, that's great. Compared to another algorithm which may give only 75% accuracy, right? So accuracy is one measure based on which I can select an algorithm, whether decision tree is doing good for my data or logistic regression is doing good for my data, right? Again, accuracy is only one measure. There are a couple of other important measures as well, like precision and recall. There are slight differences between these different measures, but you have a bunch of different measures. And based on those measures, select your algorithm. What algorithms we need in data science? That's a great question as well. There are some fundamental techniques, okay, that every data scientist must know. These are like basic techniques for doing anything. And it not just teach you technique, but also different concepts. Like decision tree is teaching you the concept of entropy, right? So those fundamental concepts, these techniques will teach you. Something like k-means clustering, decision trees, linear regression, naive Bayes. So there are a bunch of fundamental techniques that any data scientist must know. And you can easily get this list if you open up any university's data science class. If you look at their outline, you can find out what are the basic algorithms. Okay. And then on top of it, there are many complex variations of these techniques, and it's an ocean, right? The more you learn, the more it will be. And even in decision trees, you can go into the math, and then there's a lot of complexities on decision trees itself. Okay, entropy is one intuitive way of figuring it out, but there are 20 different ways people have found out how to choose an attribute. Instead of entropy, somebody says, look at something called as minimum description length. That's another metric. Just like an entropy, minimum description length is a different measure. So based on that, you can build a decision tree, right? Now, as a data scientist, you can choose for your problem whether this way makes better or this makes sense, right? So there's complexities, layers of complexities for any given thing. But as a basic introduction, there are a bunch of techniques that every data scientist should know. Okay, very good. So now let's look at simple demo. So this is an R language similar to Python, if you're familiar with that. So similar things you can also do in Python as well. But R is more kind of statistician and mathematician oriented language than Python. Python is more computer science oriented language. So I have this data set in a CSV file, diabetes.csv. So let's read it and view that data. So this is a data set in a tabular format, okay, which are a bunch of columns. This data set is it's a real data set, by the way, but it's a very small data set, okay. Total it has, I guess, few hundred records. And what does this data set represent? It's a data set about women patients who has participated in some diabetic study, okay. And for these patients, they collected different features, okay, things like number of times a particular woman got pregnant, and what's the glucose concentration in her blood, diastolic blood pressure, skin fold thickness, serum insulin level, body mass index, diabetes predictory function, like family history of diabetes, right, age, and then finally the column that we want to predict, whether this particular patient has risk of diabetes or not. Okay, so that's the column that we are planning to predict. Given a profile of a patient, we want to predict whether that particular patient has a risk of diabetes or not. And depending on that risk, I can probably take some preventive measures, right? If a patient's risk is very high, then we may want to control her diet very strictly, or start taking some medication, do some preventive actions, right? So that's the advantage of predicting ahead of time. And we're going to predict that based on all these different columns. Okay, that's the problem definition. So that's my data, and that's our goal, to build a decision tree, to be even specific, that can predict whether the person is going to have risk of diabetes or not. Okay, now for that, of course, we can run our algorithm that we just learned using the entropy and then build a model. Great. But then how do I know this is good or not? Like as I think Praveen asked, how can I select whether, how can I decide this algorithm is good or not? We said find the accuracy. But how do we find the accuracy? We used all the data that is available to training itself. So I have to test the model as well, right? It's like in our classes, they don't give you like all the examples in the class itself, right? The teacher nicely holds back certain examples and then gives those questions on the exam, right? If they give you same question in the exam as what you saw in the class, everybody scores well. So you're not really testing the learning capability. Instead, you show some examples in the training while learning, but then you show some other new examples in the exam to test, right? To test the ability of your mental model, how well it learned the concept. So in a similar idea, for a given data set, you first always divide your data into two subsets. One is a training set, another one is a testing set. Okay? And using the training set, you build your model. That means you practice and then build your mental model. Okay? And once you find the model, you evaluate that model, how good that model is using the testing data set. Right? In the testing data sets, since we derived it from the original data, we also have the real answer associated with it. And then the model is going to predict something, and then you can check how well you are doing. It's like for the questions that are given in the exam, the teacher already knows the answer key. But then based on the answers that you gave, he can match how well it aligned with the answer key and then give you a percentage, right? That's like accuracy of the mental model that you built, exactly the same way. Okay, so we're going to divide our data set into training and testing. And there are a bunch of different ways. In Python, you can do in some way. In R, you can do in some way. In other language, you can do it in a different way. Okay, and in this example, I'm going to use one particular method of dividing training and testing. So if I look at it, n row of diabet, that's my original data, total of 768 records. But then I randomly split into training and testing. Now if I see n row of diabet train, that's 529 records, and test 239 records. So randomly, I divided the 768 dataset into two parts, one containing 529, another containing 239. Okay, and then I'm going to build a model using the training dataset, and then I'm going to test it using the test dataset. Okay, and for training, I need to have some implementation of the algorithm, right? Something like whatever entropy that we have seen. And that kind of an implementation is already available for me, implemented by someone else. Okay, it's called as a package. Okay, the package that you can just import and then start using the methods that are implemented in that particular package. And that package for decision tree is called as rpart. Rpart stands for recursive partitioning. Okay, and in that particular rpart, I have a function called rpart again. So that's the function which can learn a decision tree from a given training dataset according to some measure, not exactly entropy, but some other variant of it. Okay, and I need to tell what is my column on which I'm making predictions. In this case, has risk diabetes, and what is the data using which I'm training my model. Okay, and there are a bunch of other properties as well, other parameters that the function can take. But at the minimum, you need to give this. What's the data from which you are learning, and what's the column that you are trying to predict. Okay, so that's the model. And you can print out that model, and it looks like this. So at the root node, you have all the 529 records. And then first you want to check plasma glucose concentration. If it is less than 154.5, then you check body mass index. Less than 26 or greater than 26, like that. Okay, so it's like a tree structure, but we can actually plot it as a tree and then visualize it as well. Okay, that's the other two things I'm doing here. It looks like that. Okay, I'm not actually explaining individual syntax or anything. I'm just telling you what we are trying to do. So that's a decision tree that we constructed. What is a decision tree telling us? First, it is asking me to check the glucose concentration. It figured out that glucose concentration is the most important thing to make a prediction of diabetes in this case. Okay, so I'm checking glucose concentration, which is probably intuitive also, right? We all know that glucose level is very, very important indicator of diabetes. If it is less than 154, you go to the left. If it is greater, you go to the right. And if I'm going to the right, that means my glucose is very high, glucose level. And then I'm checking age. If age is greater than 53.5, that means kind of elderly woman, then I can pretty much directly say that this person has a high risk of diabetes. That's again kind of intuitive, given our general knowledge of diabetes. If an elderly person has high glucose concentration, then pretty much we can say it has a risk of diabetes. And if the age is less than that, we are saying no, again based on the data. And if the glucose concentration is less, then we are going to check body mass index. Okay, if it is less than 26, then we are saying no. So that means your body mass index is low and your glucose concentration is also low. So pretty much you are healthy. So no risk of diabetes, like that. So bunch of decision tree that it created. Now this is the model that we built from the data. Now we need to evaluate it. Okay, how good this model is. And for that, we are going to use our test data, the portion of the data set that we kept aside, right? And what are we going to do? We're going to use this model, apply it on testing data, and then get some predictions. What are the predictions according to this particular model? And then we are going to verify how well they match with the actual results that we already know, right? So there's a particular function called predict to make predictions. For that, you provide what's the model using which you are making predictions and what's the data set on which you want to make a prediction. Okay. Now, if you see, it shows you basically a bunch of yes/nos. These are the predictions that I made. But then I also know the actual values of this records, right? That is basically dollar has risk diabetes. These are the actual values. So these are my predicted values. These are my actual values. So it's like a answer sheet, right? This is the answer key, yes, no, yes, no. And these are the answers given by a student. Now we can match. We can say how many he got right, how many he got wrong. That's the accuracy or percentage, right? And to do that also, there is a notion of a confusion matrix. Okay, it's like this. The actual answers are here, the predicted answers are here. So we got 123 and 47, meaning there are 123 questions or test records for which the model said no, and also the actual answer is also no. And then there are 47 questions where the model said yes, and the actual answer is also yes. So 123 plus 47 are the right number of questions on which the model did. These are the number of questions on which the model did right. So my accuracy is 123 plus 47 divided by the total 239, which is, if you compute it, it becomes 0.7113. So 71.13%. So that means if I use this model in production, I would get roughly 71% accuracy. Out of 100 patients I make prediction, 71% I get right. The remaining, I'm going to make some mistakes. Make sense, everyone? So that's the accuracy. And similarly, there are a bunch of other measures as well. Like these are all the different other measures that people may be interested in. Like confidence interval is one thing, sensitivity, specificity. There are a bunch of other things. Each one has a different flavor and the type of information that it captures. And depending on the application, one measure may be important than the other measure. Okay. And that we will learn when we try to understand each of the measure. Okay, but the point is, for the given model, you can come up with these kind of accuracy or some other measure, and then based on that, you can compare among other algorithms and then choose the best one that is available in your toolbox. Okay, so that's kind of the life cycle of building a model and then evaluating a model. Again, all of this is just scratching the surface of model building, and in each of the stage you can go deeper and then get more complexities and learn different layers of these algorithms and evaluation techniques and data preparation and all that. Okay, so that's actually pretty much what I have. The remaining slides are essentially just demo itself. That's how you read the data and then divide it into training and testing. As we said, training to train the model, testing to validate and make predictions, and then evaluate the model. And then you actually do the implementation of the model. Either you implement on your own or use some existing implementations to build the model. Okay, and then you may want to visualize the model depending on the model, of course. And then finally, you validate how well you are doing for that particular model. And that's the accuracy of the model finally. Okay, and that's it. That would be the end of one model. And sometimes if the accuracy is bad, then the immediate question is, oh, how can I improve it, right? Maybe you feed better data, or you tune some parameters of the algorithm. Every algorithm comes with certain parameters, okay? And then you can tune those parameters to do a better fit. Or you may want to add some new data, okay? You go to a diabetic specialist and then show your problem setting. I'm using these columns, and then I'm trying to make prediction. Then diabetic expert might say, oh, recent study showed that the number of times you eat in a day also makes a difference. Okay, then maybe you want to go back and then add another column in your data, number of times person eats in a day. Okay, that would be another column, and maybe you get better results by adding that column. Okay, so you may change the data, you may change the algorithm, you may change the parameters of the algorithm. There are multiple things you can do to improve your performance of your yes, accuracy is the simplest factor everybody can understand. So that's why I gave you accuracy as one measure, but there are other measures as well. Like if you look at our demo, just to give you a hint, there are, so 123 plus 47, we got them right. But at the same time, we made some mistakes as well. The model made some mistakes. And there are also two types of mistakes. And if you notice, there are 24 questions where the model said yes, but the actual answer is no. What does that mean? The patient is fine, actually, but the model said, oh, this patient has a risk of diabetes. So it's a false alarm. It's called as false positive. Okay? So that's 24 of those. And then there are 45 patients or 45 questions for which the model said no, but the actual said yes. That means the patient indeed has a risk of diabetes, but our model said, no, these guys are fine, don't need to worry, right? And if you look at it, there's a different cost for a different mistake. Like in this case, 24 case, what's the worst can happen? You're mistakenly saying somebody has risk of diabetes. The max that they do is they go for a more detailed test, or they do some dieting or something like that. Hopefully they don't take medicine yet, but they do certain steps. Maybe at that level, it's a less risky mistake, right? Maximum they go to a second test and then say, oh, you're fine, and then everything is okay. Whereas these guys, they had the risk of diabetes, but you're saying, no, you're fine. And that may be a costly mistake, right? Costly meaning there's higher impact because their disease will not get recognized. They will think all fine and they continue their living style, but then the problem may aggravate and then they have some other problems in future, right? So the point is, different types of mistakes have different cost associated with it in your business. Again, what's the cost of saying somebody is less risky to give a loan, whereas he could not have paid the loan at all? Or the other way around, he was very good borrower, but you said, oh, this guy does not has high risk, and then ignored them, right? What's the cost? Different decisions will cost you differently, right? And then in those cases, accuracy may not be the best measure, because accuracy says all types of mistakes are of equal cost. Whether you do false alarm or whether you miss the actual diabetic patient, they are all of equal cost. If your application is like that, then yes, accuracy is a good measure. But typically, you have different costs for different mistakes. And depending on your application, you may choose a different measure that gives you higher priority for the high cost mistakes and lower priority for the low cost mistakes. Okay, so that's just one flavor, but then there are other aspects to these as well. Make sense? Okay, so that's pretty much about what I had to say in the webinar. And of course, this webinar is sponsored by Edureka, and we offer a course on data science as well. And I often teach it, and along with other highly qualified instructors. And if you're interested in learning more, definitely consider taking this class. With that, I'm finished with what I wanted to say. Now, if you have any kind of other questions, I'm happy to answer. Okay. Bye, everyone. Thanks for attending the webinar. See you and good luck.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!